Hey, good morning. Good morning, students. Okay, I need to make this bigger somehow. What's the secret? Pin video. That's the secret. Ah, come on. Yeah, there we go. Well, let's see. We've got Bear with us this morning. Let's see who else we've got here. Bear, it's just you and me right now.
Good morning, sir.
Yeah. Well, welcome to whatever day this is. It's June 22nd. I don't know if that's got any interesting thing in history or not.
Sir, if you don't mind, do you think I could ask about PV diagrams real quick?
Yeah,
I
go
seem
ahead. That's what I'm here for. Yeah.
I seem to be like a little confused on when to draw like PV diagrams using like a vapor dome or the hyperbolic curve um or like sometimes just like how to tell what to use in a PV diagram per se.
I'm so glad you asked, Bear. Here's the dirty little secret. If it's, let me kick that out of there. If, wait a minute, I need to adjust this. There, that's pretty good. Yeah, that's decent. If you have a real, what we'll call it a real gas, and you draw a PV diagram, it's going to have this vapor dome. If you have an ideal gas, it's not going to have that. It's going to have these hyperbolic isotherms. Uh-oh. Something just happened here. Hey, I've got another customer though. Stuart just tuned in. Good deal. Yeah. Stuart the Bear asked me, when do you draw these vapor domes and when do you not draw vapor domes? And here's the answer. If you have an ideal gas, you don't draw a vapor dome, but you draw the isotherms. They really should be in red. Here, let's see if we can make these red. There we go. I made them red. See, that's a PV diagram. There you go with an ideal gas. But if you have a substance that can turn to liquid, you don't want to use an ideal gas law on a liquid, do you? No, we don't use the ideal gas law on liquids. I'm sorry, we just don't. Hey, but see, a real gas is, what's the word? They condense and they vaporize, or what's the word? Boiling. Can't think of it now. It's another name for boiling. Evaporate, yeah. But see, real gases, they have isotherms too, but they're kind of goofy. They have kinks in them. Here, I'll draw you one. See, they go like that. So yeah, of course they have more than one. I mean, they have hundreds of them, really. I'm just putting a couple in here so you can see. There you go. Put those in red. Get yourself a red ink pen or a pencil. Now, the next question, Bear asked this question. Let's see who else is tuned in here. See if there's anybody else on board here. Oh, yeah, we've got Parker and Stuart and Bear. We got a good crowd so far. Bear asked, when do you do this vapor dome jazz? And when do you do the hyperbolic isotherms? Well, hey, I'm going to ask you, Bear, do you understand so far?
Yes, sir.
Yeah. Now the next question is, well, how do you know whether something is an ideal gas or whether it's not? Okay, how do you know? Well, here's how you know, Bear. You go to the back of the book here, and there's all these tables, lots of tables, and there's a table here called saturated water. It's table B.1.1. If you have a saturated table, then you draw a vapor dome. And I'm going to flip again here. Now, after the water, they've got a whole bunch of water stuff here. And then they have ammonia. Can't find it. Yeah, here we go, ammonia. They have a saturated ammonia table. Well, I called it a real gas. There you go. You got saturated ammonia. It's not an ideal gas because it can go liquid. And then after that, they have a bunch of others. They have, believe it or not, carbon dioxide can liquefy. In fact, and they have a carbon dioxide table. Now, the weird thing about carbon dioxide is if you get it warm enough, like room temperature even, it's a vapor. It's not a liquid. And so for certain temperatures, you could draw those hyperbolic isotherms for carbon dioxide. They have a saturated carbon dioxide table here. But see, carbon dioxide can even be a solid. It's like water. Water can be a solid. Ice, you've had ice in your Coke or Dr. Pepper or whatever. Did you know they call it, they got a name for that, solid carbon dioxide. They call it dry ice. Have you heard? Let me ask my friend Bear. Bear, have you heard of dry ice?
Yes, sir. I've also played around with it.
Yeah. Well, see, if you have a chunk of dry ice and you put it in your punch bowl, it'll bubble. You know what those bubbles are? They're that solid carbon dioxide they don't call it evaporating, they call it sublimating. When you go from a solid to a vapor, but ice does that, or water does that. Open up your freezer in your kitchen if you got one. If you got a freezer compartment, and you'll see sort of a billowy cloud. That's an ice cloud. That's ice vapor is what it is. See, ice, water turned to solid, sublimates and turns to a vapor. Well, we answered a student's question there. Let's see who else we got on board here. Okay. I can't seem to get this. Yeah, there we go. We got a great crowd. We got crowd. We've got Roxana, Parker, Cameron, yeah, Bear, Aubrey. Let's see who else we have here. Stuart and Spencer. We got a great bunch of students here. And I think we'll, unless there's another question, now Bear asked a good question about when do you do this vapor dome thing and when do you not do a vapor dome thing? And I tried to answer it, but I'll answer any other question and then we'll start our lesson today. Anybody else have a comment or question? Well, okay. I didn't get through telling you about all those vapor dome tables back there. After carbon dioxide, I think there's a methane, and then it starts all over again for English. See, that was all SI, System International. Okay, well, I'm going to erase this, and we're going to start on today's lesson then. Okay, now let's see, what are we going to study today? We are going to study turbines and throttles. Today, the topics are turbines and throttles. That's what we're going to do. Turbines and throttles today. But before we do, let's review what we did the last time. Now, I'm sure you all know by now, if you read your Blackboard material, that you can get on YouTube and watch these wonderful lessons over and over again till you get it. Like, for instance, last Wednesday was, I think, the 17th. Today is the 22nd. I think that's right. Let's see, 17, 18, 19, 20. Yeah, that's right. And if you wanted to watch last Wednesday's lesson over, you get on the YouTube like it says there in on your Blackboard material for the course, and you can watch that over and over and over until you got it. That'd be good. But I wanted to review. We were doing a nozzle. And in fact, it was 4104E. We're doing a review here for a few minutes. I want to make sure you guys get this. We did this last Wednesday, and that was a nozzle. We'll get to turbines and throttles here in a minute, but right now we're going to do a nozzle. And remember, a nozzle is a device like this. And let's see, I'm going to pick on somebody here and see if they remember anything from the last week. I always start with Stuart. I don't know if you noticed that, Stuart, but I start by picking on you, first of all. Stuart, unmute and tell me, what is the purpose of a nozzle? Why do we have nozzles? Stuart, go for it. Purpose of a nozzle. He's thinking. He's unmuting. Earth calling
I
Stuart.
don't quite remember right now.
That's okay, Stuart. That's okay. Well, Spencer, I'll pick on Spencer then. Spencer, what is the purpose of a nozzle?
To increase the velocity of
That's
whatever's
it.
moving through it.
He's got it. The reason why we have nozzles is you come in here with a little tiny velocity, incoming velocity, but you come out with a great big exiting velocity. That's why we have nozzles. Now today we're going to study turbines. Turbines are different. The purpose of a turbine is to provide power. That's why you have turbines. They have a turbine, a water turbine at the dam, the Keystone Dam, and it spins and turns a generator and provides electricity. It provides power. That's why they have turbines. And I'll tell you about throttles when we get there. But on that problem, 4104E, we had this equation. Oops, that's an I. Now notice I wrote these in kind of a dark. Those are velocities. See that there's a, whoops, let me kick this off of here. Can't ever find this dang, what do they call this thing? A cursor? It's that little arrow. Is that called a cursor? You guys need to teach me about this stuff. That dark velocity thing there. This is the incoming and that's the exiting velocity. And I made it kind of dark or bold type, I guess you could say. So here, let me pick on somebody. Doggone it. There's this little arrow that I can scoot around. I'm going to pick on my friend Roxana. Roxana, what do they call that little arrow that I'm scooting around on my computer? Do you know the name of that thing?
Yeah, I think it's a cursor, like you were saying.
I think it's a cursor. I think you're right. Yeah. Now I'm going to, Roxana, I'm going to ask you a question now. Let me get my cursor on here. There we go. Roxana, why do I make these velocities dark like that? There's a reason. Why do I make those velocities dark, Roxana? There's a reason. I make those velocities dark.
To differentiate from the other bees
That's
that we have.
absolutely right, Roxana, because there's other V's to worry about. Name one, Roxana. Name another V.
Volume.
Yeah, there's volume. Very good. Give me some more, Roxana. You're doing great. Give me another V. She's thinking. You can do this, Roxana. There are actually 5 V's. Give me another one. Isn't it funny how your mind goes blank when
Yeah, I
somebody
can't
asks you,
remember.
somebody asks you something, and you know it. I know you know this. Roxana, there's a little bitty V. And see that little bitty V? That's different than the big V. Roxana, what's that little bitty V? She's thinking. Her mind just went blank, I guess. That's okay. That little bitty V, it's important because that's the V that's in the back of the tables. If you go back and look in your tables, you'll see those little V's all over the place. Okay, Roxana, what is that little bitty V?
I can't remember the name right now.
I'll give you a hint. It starts off SP blah 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 SP.
Oh, a specific volume.
That's it. She's got it. She's got it. It's specific. It's PE. Uh-oh. CIFIC. Specific volume. That's exactly what it is. And you can tell all these things by their units. See, that V there, that dark V is meters per second. That's velocity. But this V here, that's volume. That's cubic meters. And Roxana, one last question before I pick on somebody else. What are the units for this little V, Roxana? What are the units?
I think it's meters cubed to the kilogram, divided by kilograms.
Exactly. Good going. She knows what that is. The units for specific volume are cubic meters per kilogram. You can tell what things are by their units. The units give them away. There is one more important V for us. It's got a capital V with a dot over it. Here, let me pick on another one of my wonderful students here. Let's see. Parker. What's the name of this thing with the capital V with a dot over it? What's the name of it, Parker?
The volume flow rate.
That's it. It's the volume flow rate. And see, it has different units. It's cubic meters per second. I want you to know the names of all these things. Okay, well, let's, we're just having a little review here. And see, the thing is, I can tell that some of you need this review. Maybe you need this review. Maybe it's not hurting you a bit to review some of this stuff. Okay, well, here, let's put in the numbers and get this. Now, I did this 2 different ways. But the best way, 2 different models. The best model, this was air, I think. No, it was, well, I don't know. I better look it up. I can't remember. 104E, it was R410A. See, that's a refrigerant. That's what I have in my air conditioner for my house, R410A. And see, you can look those up. Let me find them for you. But now, wait a minute. It's in English. So you have to go to the English to find it. I'm trying to find the R. I'm having a little trouble here. It was R410A, wasn't it? Did I do that right? Let me make sure I'm doing the right thing here. I'm reviewing problem 4104E is what I'm doing. 4104E, and it says, yeah, saturated vapor R410A. Well, we got to find the R410A back here. And I'm having trouble. R410A. Aha, I found it. Yeah, but now here's my problem. How do I look up this specific enthalpy? I need to know some more information. Okay, well, let me see if I can find it here. 4104E, okay. Well, it says here, we have 1800 Rankine, 1800 Rankine coming in, and 30 PSI. Okay, well, I'm going to find that now in the back, 1800 Rankine. 30 PSI. I'm getting confused here. No. Guys, I'm doing this all wrong. This was air. And you guys are gonna have to help me. I was looking at the wrong problem. If you look at problem 4104E, it's air in that nozzle. It's not that, I was looking at the wrong problem. And so if you have 1800 Rankine, 1800 Rankine, you just look it up. Okay, well, I'm going to do that now. I'm going to find 1800 Rankine. Here it goes. All right, 1800 Rankine. $1,800. There it is. It is 449,794. 449.794. I'm on table F.5. But I need you guys to double check me on that. Now, while I look up this exiting, the exiting is 1500 Rankine. I want you to go to that table and make sure that I did that right. Okay, now I'm going to do the 1500 Rankine, and it is 1500. Oh, I'm going to have to split those because they don't have it exactly, do they? They have 1480 and 1520. So I've got to go 262.537 and 270.359, and then divide by 2. I'm getting 266.448 BTUs per pound mass. I need somebody to go to the table F.5 and make sure that I got these numbers right.
I got the same for both.
Yay, thank you. Now was that Spencer?
Yes, sir.
That was Spencer. Good. Okay. Now, see, they give you the velocity coming in. If you read the problem, they said it's 90 feet per second. 90 feet per second. So, see, we know that. And we know this. Here, I'll circle this. We know what that is. We can get this because they give us the velocity. We know that, we just looked it up. And see, this is what we're supposed to find. Well, we can find that. Look, you got an equation and you know everything except one thing. We can do that. We took algebra in school. All right. Well, let's go through that again. I need this room here. Now we're going to study turbines and throttles. Right now we're reviewing problem 4104E. So let me make some room here and we'll write this out. Okay, so here we go. We've got 449.794 BTUs per pound mass. Plus 90 feet per second squared over 2 equals 266,448. The units are the same as on the left, so I could be sloppy because I have recorded my units here. Plus So now we're going to solve that. And we're going to get our answer. And this will be the best answer using the best model. I did it 2 ways last Wednesday, but using the best model, see, these are called ideal gas integrals. And I got these numbers from the ideal gas integral tables. They have actually integrated a function for the specific enthalpy. Okay, we're going to do that and get our answer. Here goes. I just need the room here, so I'm going to say goodbye. Now, do you remember what this equation is? This is the first law of thermodynamics for nozzles. See, all the different devices have their own first law that is derived from the generalized first law of thermodynamics. Okay, well, let me show you how to use these units. I showed you this Wednesday, but I just have a bad feeling that maybe some of you didn't quite get it. Here's the thing. You got BTUs per pound mass here, and you got feet squared per second squared here, and you can't just add those two. They're not the same, and you can't add them. I think we gave you a little talk about that, like adding feet to inches. You can't add feet and inches unless you convert them both to feet or both to inches. But here's the dirty little secret. If you take a BTU per pound mass and multiply it by 778, I think it's 0.1. I can never remember. Let me look it up here and we'll see what it is. It's 778. Yeah, there it is. 778.17. That's what it is. 778.17 foot-pounds force per BTU. See, I'm going to do that to get rid of the BTUs. And then what I'm going to do is I'm going to multiply this by 32.174 pound mass feet per second squared is equal to a pound force. You'll find this number in the back of the tables. I could give you the table number if you wanted. It's, I'll tell you where it is. It's on page, well, it's Appendix A. There it is. You could look it up for yourself. That's in Appendix. It's in Appendix A. You should be familiar with this Appendix A. It's very useful. This is also given probably on that appendix, but I don't see it. Let me see if it's in there. I'm just curious. Well, I don't see it there in that particular place, but I know where it is. It's on page 9 in your book, and you can find this. Yeah, there it is. It's on page 9. If you multiply this by yeah, 32.174, that's on page 9. Pretty sure it is. Yeah, there it is. This is on page 9 of your book. And now here's the beautiful thing. Do you see those BTUs? They're going to cancel. Do you see that pound force? It's going to cancel. Do you see that pound mass? It's going to cancel. And what will you have left? Well, you'll have feet squared per second squared. Ooh. If you multiply this number by these two numbers, you'll convert that to feet squared per second squared. Same with this one. I didn't give myself enough room, but see what you have to do is you have to multiply this number by 778.17, and then you have to multiply it also by 32.174. But you have to do the same thing to this number. See, that's in BTUs per pound mass. So you got to multiply that number by 778.17, and you have to multiply that number by 32.174. Okay, now, we did this last Wednesday, and we're having a review here. But I'm going to take 2 minutes out, and I'll shut up, and I'm going to get my calculator out. And I'm going to multiply that number by that number by that number. Then I'm going to add this number to it. And then I'm going to multiply that number by that number by that number and subtract it from that. And then that's all that's going to be left on the right-hand side of the equation. I'm going to solve for the exiting velocity. So I'm going to shut up, and I want you, well, we're going to see if we get the same answer. And this will be the best answer because we're using the best model. Okay, on your mark, get set, go. You have 1.5 minutes to plug all that in, and we're going to see if we get the right answer. Here we go. I must have done something wrong. I'm not getting the right answer. Let me try it again here. Must have done something wrong. Okay, I'm not getting the right answer. I must be doing something wrong, doggone it. Wonder. I wonder what I'm doing wrong. This number's wrong. Let me look that number up back up again, guys. I've got to have you guys double check this stuff. Now we're looking at air at 1500, I believe is what it was supposed to be. 1500, where the heck are you? Air 1500. There we go. And at 1500, see it, it's 1800 coming in, right? And at 1800, okay, now just a minute now. We're in English. 1800 coming in, it's 449, 794. I got that number right. But at 1500 going out, that number is wrong. I don't know what I did. Wonder how the heck I got that.
I think what you and I both did was we used the U values instead of the H values for the calculation.
Well, let's do it right. Yeah. Yeah, that's exactly what I did. Okay, now let me get this right. Okay. This number, I believe I got right now. That was wrong. Whatever that number is, you still have to multiply it by this stuff. But I'm getting 369.28. And I believe that's going to be okay. Yeah, I had that wrong. Now I have it correct. And now please put all that in your calculators and get the answer. And I had the wrong number. Got the right number this time. I'm getting an exiting velocity of 2009.9 feet per second. Now, go ahead and take another 15 seconds and finish that off. And I want to hear some uh-hs.
That's what I got.
Good deal. That is the correct answer. And we got that answer last Wednesday. I don't know what I did with this number here. I had the wrong number, but we got it right this time. Now I did it a different method last Wednesday. The other method or model, I should say, there's this happy face model that I just did where you look up these values of H in the tables, and delta H is you just look these up in the tables. It's pretty simple and pretty easy. But the other model, which is not as good, and I did this Wednesday, is when you go like this. And what I used for the C sub P was the C sub P at room temperature. Well, this is not at room temperature. You're coming in, I think, at 1800 Rankine, and you're going out at 1500 Rankine. Guys, that is not room temperature. That's really hot. And so that's how come you don't get the right answer. However, it wasn't terrible. I forget what it was using the other model, but it was in the ballpark. And you can use other models. Hopefully you'll use the best model, but some models are better than others. Okay, that's enough review on the nozzles. And now we're going to talk about turbines and something else, throttles. Is there any comment or question on our little review section here? I'm listening. Okay, well, if you're happy. Okay, I'm going to erase all this. Now let's write the first law of thermodynamics for controlled volumes. This is the generalized or the general equation that works for anything. Now, sometimes this is a summation. But sometimes it's not. For a simple problem, if you just have one inlet and one outlet, you don't need the summation sign. Now, I want you guys, see, that is the first law of thermodynamics for a control volume. And we told you what a control volume was well, I think I've told you several times. But here, let me pick on somebody. I need this wonderful student, Cameron. Come in, Cameron. Earth calling Cameron. And Cameron, unmute and tell everybody what a control volume is. What's a control volume? Who's calling Cameron? Come in, Cameron.
That's a great question.
Yeah, this equation here is for control volumes. It'd be nice to know what a control volume is. Cameron can't remember right now. Let's go to Bear. Bear, what's a control volume? Unmute and tell me what you think. What do you think, Bear? Control volume.
Is a control volume like what you use just as a basis for whatever you're working with?
Yeah, but what is a control volume? What is it?
I'd have to say I don't know.
That's an honest answer. You have to know what this is. What it is, Bear, it's a volume with mass in it that has mass coming in to the volume and mass going out. Now, you might have just mass coming in and no mass going out, or you might have no mass coming in, but mass going out. But you do have mass either coming in and going out, or one or the other. You got mass coming in or out. That's what a control volume is. And today's topic is a particular control volume called a turbine. Now here's the symbol for the device sketch, and you have M dot I coming in and M dot E going out, and you have an output of power going out, and we're going to do a problem. And the problem we're going to do is, let's see, I'm going to do a turbine. We're going to do 425. 425. We're going to do problem number 425. But before we do, I'm going to ask another wonderful student. We'll go back to Stuart. I'm always picking on Stuart. Stuart, what is the purpose of a turbine? What's the purpose of a turbine? All these
To generate electricity.
That's it. You got it. Good going. Good going. It's to provide power of some kind. Now, usually it will result in electricity, but it doesn't have to necessarily be electricity. We're talking power in some form for the output. It provides you with power. Okay, now here we're going to do this. This is 425, and they said, if you read it, a steam turbine. Well, if it's a steam turbine, we're dealing with H2O, has an inlet of 3 kilograms per second. They said coming in, you've got 3 kilograms per second. 3 kilograms per second. Now, what is that what are they talking about? You can tell what stuff is by the units. Whatever this 3 is, it's kilograms per second. Let's go to my friend Spencer. Spencer, what's the name of this 3 kilograms per second? It's giving you something. What is it?
It's the mass flow rate.
That's it. That's it. That's what this is. It's the incoming mass flow rate. Good going. Okay, now what else do we need to know here? Let's see. 12 coming in, we got 1200 kilopascals. And 350 C. 350, that's coming in. And a velocity of 15 meters a second. Man, we know a lot of stuff about the incoming. All right, the exiting is at 100 kilopascal and 150 Celsius. 150 Celsius. Okay. Very low velocity. Find the specific work and the power. Okay. They want us to find the power and the specific work. What they mean is that little w. See, what they want is a big W dot. No. Yeah. They want the big W dot and the little w. That's what they want. Okay. Well, there's our device sketch. And now the next person I'm going to ask is going to be Roxana. I just keep going down the list here, but I don't know what to ask you yet, Roxana. We'll figure out something. There's the device sketch. Now we always do a PV diagram. So why don't we do that? That'd be fun. Here goes. We're going to do a PV diagram. Yeah, I know what to ask Roxana. Roxana, do I put a vapor dome on this, or do I put those hyperbolic isotherms? Roxana, you got a 50-50 chance of getting this right. Which do I do, Roxana? Vapor dome or ideal gas isotherms? Go for
Vapor dome.
Vapor dome, good going. You do a vapor dome, that's right. Because it's water. It's water. And water is not an ideal gas. Okay, well, let's locate, we need to find where we are. Well, let's draw the 350 Celsius isotherm, shall we? And I happen to know that the top of this vapor dome is like 374, 350 is up here towards the top. Here, I'll draw the 350. That's the 350. Now, how do I know that? Well, go back. Go back and look in the water tables back here. Help me find that. Look on page table. Look on table B.1.1. Do you see where they have the isotherm at the very top is 374? Go back there and look. Well, see, 350 is pretty close to the top. So we know we're on that isotherm. Now the pressure here at the top is something like 22 megapascals. Or yeah, 22 megapascals. But we're just 1200. Holy cow, that's down here pretty low. So here we go. We'll say 20 or 1200 kilopascal. You know where we are? We're right there. We have just located state one. Now, we've got to draw the process. Here's the rule. If you have a process, and we do because we're going from state one, here, let's put a 1 here, to state 2. We'll put a 2 there. Or you could say the state is the incoming and the exiting. You put an I and an E there if that makes you happy. You put an I and an E there. There you go. So if the rule is, if you have a process, and we do, we're going from state 1 to state 2, then you must draw the process on a PV diagram. Well, here's our PV diagram. You don't do the one with the ideal gas because we don't have an ideal gas. But where is state 2? Well, it's 150 Celsius. Well, where is that? Well, here, let me kind of fudge this a little bit. And we'll put 150 in here. You know what? 150 is colder than 350. It's down here someplace. I just drew the 150 Celsius isotherm. Now we're on that, but we're at 100 kilopascals. Well, I'm curious, what's the what is this pressure here for the 150? The 150 is pressure of 475.9. If you wanted to know what this pressure is right here, it's 475.9. I'm looking at table B.1.1, and that's what it says. Yeah, I did that right. But see, we're at 100 kilopascals. Well, you know, 100 is smaller than 475. It's more down here someplace. And so here we are right here. Here's your state 2. Here's your state. Here's your process. There you go. Put an arrowhead on it. We have just drawn our process on a PV diagram. Well, so what? Well, we did our device sketch and we did our PV diagram. And what's next? Well, next we have to write our first law. Now this is a turbine. Okay. It's a turbine. So we're just going to go through here and write this stuff. Here we go. We're doing problem 425. I need a little room here. We're doing problem 425. So let me erase that. I need the room here. Now this first term is going to be 0. I might have to erase some of this in order to fit it in. That first term is 0. Now we're going to ask one of my wonderful students why that first term is 0. Let me go, here we go. I'll move that cursor around. I think I'm on Parker now. I might have missed somebody, but Parker, why is the first derivative of your total energy with respect to time 0? Why is that, Parker?
I remember you saying something.
Yeah. I'll give you a hint. You could say the answer has something to do with S dot, S dot. Do you remember what that was, Parker?
Not right now.
That's okay. You're here to learn. But can you think of why that the total energy inside here, inside this control volume, is not changing with time. Why is that? Why is the energy staying the same? An hour later, a day later? How come it's not changing any? Parker? Parker, this turbine's sitting there and it's running. It's making a noise. It's going, and it's been doing that for days, okay? You come back 2 days later and it's going, same noise. And if you check the gauges, the pressure coming in and everything, it stays the same. See that pressure, that 1200? It's 1200 kilopascals coming in. An hour later, it's still 1200 kilopascals. A day later, this thing is just running. Nothing's changing.
Mm-hmm.
Nothing's changing with time. Nothing. All the properties are staying the same. They call that, Parker, they have a name for that. It's S dot S dot. What is that? Put Parker on the spot there. Parker, that's called, go ahead. It's
I
got
don't
a
know what
name.
that is.
Say again.
I don't know what that is.
That's okay. You're gonna know because I'm gonna tell you. It's steady state. Steady state. What that means is the state, which I hope you remember, is all of the properties. The state is all of the properties. The properties describe the state of your mass inside your control volume. And it's steady. Everything's steady. The pressure's steady coming in, temperature steady coming in. See, the temperature coming in, Parker, is 350 Celsius. And later it's still 350. This turbine is providing power. And some of these run for days. They have a great big turbine that's providing us with electricity. Parker, are there lights on inside your house right now?
Yeah.
Yeah, you know what? Those lights are being provided with electricity from a great big old turbine. A turbine bigger than the room you're in, okay? It's a big turbine. It's spinning. Parker, do you know how fast it's spinning?
I have no clue.
It's spinning 60 cycles per second. It turns around 60 times every second. They call it 60 hertz. In Europe, the turbines spin at 50 hertz and is providing you with the electricity for the lights in your house. But it's been turning that way all morning, and it'll be turning that way all afternoon. Some of these do that for days. Sometimes they have to shut them down, but they have a spare. They have 2 turbines. They're huge things. And when it's time to switch turbines, they have to start up the other turbine and get it ready. And then they switch over, usually in the middle of the night. Sometimes you can be reading a book at 3 a.m. and the lights kind of flicker a little bit, almost go out, and then they come back on. They just switch turbines. Unmute and tell me if anybody's ever noticed that. In the middle of the night, lights kind of flicker, go out momentarily and come back on. Is there anybody out there that's ever experienced that? Go ahead, I'm listening.
I've seen that before.
Possibly.
Sometimes sometimes there's a problem, and they got to make repairs. There's a problem. Maybe one of the blades, they threw a blade on the turbine, and they're going to have to replace it. So they have to shut. That's why they have two of them. They'll shut one down. They'll turn the other one on, because see, if one of those little tiny blades is damaged or falls off, it could throw things out of balance. You don't want that thing thrown out of balance. That could be bad. Okay, well, that's zero, and I hope you understand it, because nothing's changing with time. Now, on this turbine here, on this problem, this is zero. It's not always going to be zero, because these turbines do get hot, and they do have a small heat transfer rate out. But in this problem, we'll just assume that it doesn't, that there's no heat transfer in or out. If that's the case, they have a fancy name for that. Let me just tell you what it is. It's called adiabatic. It's one of our processes, a very important process that we're going to study in detail. And all it means is that there is no heat transfer. You could put a dot over it if you wanted, because if there's no heat transfer, there's no heat transfer rate. That's that fancy name, adiabatic. But now you don't throw this term out. This term has a name. I told you what it was, but you might have forgotten. Let me pick on some. I enjoy picking on you guys. See, I'm just kind of a mean guy. Bear, I think we're back to Bear. Bear, I love embarrassing you, Bear. Can you remember what I told you, what that thing is? It's got a name, and I'll give you a hint. It starts with P. That W dot has got a name. It starts with P. Go for it, Bear. He's thinking. Maybe he took a break. He's probably fixing his coffee or something. We got to know the names of all this stuff. That there is what it is it's work per time. See, W is work. And if you divide by time, you'll get W dot. The dot means you're dealing with time. Now, we'll pick on somebody else. Bear's probably fixing his coffee or whatever. We'll go back to Stuart. Stuart, I'm picking on you. What's the name of this?
Power.
Power. It's power. That's why you have turbines, to provide power. Can't throw that away. Now, we don't need this stinking summation sign. There's only one inlet. And they told us it was, oh, gee, I think I erased it. Let me see if I can find it here. This, I forgot what we're doing. Oh, we're doing problem 425. And what we have is this is 3 kilograms per second. That's what it is. Okay. And then we're going to look up the specific enthalpy at 1200 kilopascals, 350 C. So help me shop around. 1200 kilopascals. Trying to find it here in the tables. 1200 kilopascal. There it is. 1200 kilopascals. 300 C? No, 350 C. Okay, I found it, guys. It says here, this number right here is 3045.8. 3045.8 kilojoules per kilogram. I'm on table B.1.3. Table B.1.3. And I'm going to wait till I hear a couple of uh-huhs from my wonderful students. Can you find that number on table B.1.3? I'll shut up. Can you find it? I'm listening for an uh-huh. I need 2 of them. 1200 kilopascals. 350 C. Can you find it? Uh-oh. I got the wrong number, didn't I? Okay, well, let me put the right number in there. I put the wrong number in there. That's why you're probably having trouble. It's 3153.59. 3153.59. Now I'm listening for an uh-huh.
Uh-huh.
I heard one. I need another one. 315. Got it. We by Jove, we've got it. Okay, that's on table B.1.3 plus. Now what's the 15? It's 15. Need to make some room here. 15 meters a second squared over 2. We're going to forget this term. Just forget that term for this problem because this turbine is not going up or down, okay? It's not going uphill or downhill. And then we have to subtract the 3 kilograms per second. I've already put my units in, so I can be a little bit lazy. But I need to know this exiting specific enthalpy. So I need to go to 100 kilopascals and 150 C. By Jove, there it is. It's a 277,638. And did they say the exiting velocity is small on this problem?
Yeah, they said it was very small.
Okay. Yeah, so you can just, on this particular problem, you can cross out those. And so here's our equation. And we're going to solve it here in a minute. We've done our PV diagram with the process. See, this is the process. We've put it on there. Put on, and we're going to find this power for this turbine. We got all the numbers. There's only one unknown, but there is one little problem, and that's the units. I need some room to operate here. Let me just make some room. We'll make some room. We're almost done with this problem. It's a turbine. It happens to have water in it. Steam. We're talking about steam, really. Now here's the problem. This is kilojoules per kilogram, and that's meters per second squared. Who am I going to ask next? Let's see. I think it's Roxana if I have another question here. No, wait a minute. I'm getting mixed up on who I've done. Okay, we've got to make the same units. Now here's how you have to do it. It turns out that a kilojoule per kilogram, here, let me just go through it, is a kilonewton meter. You know that. You know that a joule is a Newton meter, don't you? See, a kilojoule is a kilonewton meter, and a Newton is a kilogram meter per second squared. Can you see that the kilograms cancel? And what you're left with is a kilometer squared per second squared. Can you see that a kilojoule per kilogram is equal to a kilometer squared per second squared? Well, this is not a kilometer squared per second squared. It's just a meter squared per second squared. So here's what you have to do. You have to multiply this by K over 1,000. There is no exiting kinetic energy, so you don't have to, only there do you have to do that. But if you don't do that, you won't get the right answer. Okay, here's what I want you to do. We have a lovely equation, and we're going to solve for the power. We know everything, but without putting this in, it's not going to work. Okay, I'm going to be quiet, and I want you to solve that. All right, on your mark, get set, go. Find the power for me. There's your equation. See if you can do it. Well, I get an answer. I wonder if it's right. Let me look up my answer and see if that's right. Yep, that's right. Okay. Is anybody out there? Is there anybody out there that has the power that solved this equation and can tell me what they think the power is?
I got 1,253.13.
I didn't get that. I got something close in the ballpark. Do yours again. I'll do mine again. Was that Spencer?
No, that was Bear.
Bear. Nice try, Bear, but I want you to try it again because I think I got, see, I'm getting the answer in the answer book, Bear, so I think I did it right. Do yours again. Bear, take 15 squared and divide it by 2,000. Okay? That's probably where your problem is.
I got 1,128.97.
That's even closer to what I got, but it's a little tiny bit off. Now who was that?
That was Stewart.
Stuart. Stuart, you're dang close. I wonder why you're getting something different. Do it again, Stuart. I'm going to do mine again.
I got 1131.97.
Well, I tell you what I got. I got 1131.7. Now who was that?
Spencer.
Spencer. I don't know why yours is a teeny tiny bit different than mine. Let me do mine again.
After I redid it, I got 1,131.74.
Yeah. You have to do all these together before you multiply by the 3. I think that's what you get. But now, was that Spencer? Am I talking to Spencer?
That last one was Bear.
Bear, I'm sorry, Bear. Now, Bear, I need to know what the units are on this 1131.7. What are the units? See, without the units, it's sort of like, Bear, how tall are you? Well, I'm, I don't know, 70. Well, 70 what? Well, I guess inches, maybe. I don't know. You got to have units or it's worthless. What do you think the units are, Bear?
Wouldn't that be like joule per second?
That's an intelligent answer, but it's kilojoules per second. It's kilojoules per second. Let me go through that with you. Well, you can see it. Bear, look. See those kilograms cancel, and you'll have a kilojoule per second. See it? And there's another name for that, Bear. A kilojoule per second is called a what? What is it called? Kilojoule per second's got its own name. A kilojoule per second. Now, if you put that for your answer, I'd give you full credit if you're doing a test or something. But it's a kilojoule per second. Now, what's a joule per second, Bear? It's got a name, joule per second. What's it called?
Work per time.
Yeah, but what are the units for work per time? The units. You know, like the units for distance is meters. What are the units for work per time?
Watt.
You got it. It's a kilowatt. So the answer here is 1131.7 kilowatts. Good going. Okay, well, any questions on that? We did just had a senior moment. What did we just do? We just did a turbine. That's what we just did. And we got the power. It's in kilowatts. And I showed you how to do it. We did a PV diagram. We put the process on it. We did a device sketch. And we labeled it. We put a lot of information on the device sketch. And then we wrote the first law for control volumes, because see, a turbine has mass going in and out, so it's a controlled volume. We wrote the first law. What was tricky is we had to convert the units to the same thing, because when you add things, they have to be the same. So we did that and we got the right answer. Is there any question on the turbine? We did problem 425. Any last comments before we go on to the next thing?
My answer is still a little off, and I'm not quite sure where it went off.
Well, let me do it. Here we go. Now, who was this? Is that Spencer again?
This is Stewart.
Stuart. Okay, Stuart. I'm going to do this now. I'm going to go 3,153.59 plus 15 squared divided by 2,000. See, that's 15 squared divided by 2,000. And then I'm going to multiply that by 3. And then I'm going to subtract 3 times 2776.38. And here's what I'm getting. Well, I got what one of my other wonderful students got. I'm getting 1131.9 this time. Is that what you got, Stuart?
I'm getting like 1131.9675.
Yeah, that's exactly what I got. 1131.9675. That's exactly what I got. And Stuart, I think you're right. And I think I was off a tiny bit, and I'm proud of you. Anybody else? Comment or question on that? Okay, well, let's see. Let me erase all this, and we're going to move on to the next exciting topic. I want to leave this up there, though. That's your general equation for your first law of thermodynamics for control volumes. Now we're going to do a different topic here, unless you have another comment or question. And the topic now is throttles. We are going to talk about throttles, but I think it's time to take a 10-minute break, personally. We're going to take a 10-minute. So at about 5 after 10, we'll be back for more fun, and we'll talk about throttles. But right now, go stretch. Go stretch, do whatever you need to do, and we'll be back in 10 minutes to talk about throttles. Okay. Go stretch. We all need to stretch.
So you end up with all, let's put it this way, emotionally, the two of them together were a big mishmash of not good things. Yes. She, well, in that instance, she had a spirit of unforgiveness, and I don't know that she, to this day, feels like she was treated right. And you know, it's one of those things. It's one of those things you look back on, and it was like, well, that was just a fiasco from the get-go, and a family trying to honor another family member. And a big portion of the fault goes to Ryan.
Well, let's see. Is it time? Yeah, it's almost time for throttles, isn't it? Okay. Well, I wonder how many people are back. Let's see. We got a good crowd there. I don't know if they, like me, maybe they're gone to get some orange juice or something. But let's talk about throttles. Now, there's a picture of a throttle in here someplace. Let's see if I can find it. We're going to try to find it. What chapter are we in? We're in chapter 4, aren't we? Yeah, I think so. Do they? Yeah, there's a throttle. And there's a picture of one. Okay. Now you have a throttle in your air conditioner in your car, only they have a different name for it. If you go and try to buy the part at the parts place, it's called an expansion valve. And there's a symbol for it. I'm on page 123 in my book, and there's a picture of the device sketch. Basically, it's just a tube with a constriction in it. if you were to look down, it's like a piece of pipe, and somebody has, it's like they've welded a washer in there. Here, looking down, if you're looking down through the pipe, somebody has taken a big washer and they've just welded it there. So the air comes in here, or well, not air, it'd be the refrigerant. But you could have a throttle with air or anything else really. And it comes in here and then it enters this constriction here, and it causes a lot of eddy currents and spiraling around of the stuff. It doesn't have this smooth laminar flow that it did have coming in, and you're looking at a throttle. Okay, and there's a picture of it, the throttling process. Now, if you go through this first law of thermodynamics, this throttle is sitting there, and if your air conditioner is running, you probably go for a ride or something in the summer. You have that thing running for a while, maybe for 40 minutes. But the energy inside your expansion valve there is not changing any, so it's a steady state device, and so that's zero. And throttles are what we call adiabatic. They don't really have a heat transfer with the environment. So this equation becomes 0 equals 0 minus 0. They don't do any work. They don't provide power, and they don't require any power. All you're doing is sending maybe some fluid or some vapor through a constriction. So you don't need any power. And so you don't need any sigma signs because there's just one inlet and one exit. See, I had my my expansion valve go out in my, I think it was a Toyota Camry that I had. And I went to the mechanic and he wanted several $100s. This is a very simple part. It's just that the labor you have to take everything apart, and it takes time. And I forget what he wanted, $300 or something. And I just said, well, forget it. And I drove all that summer with no air conditioning. But what I did was I used my 460 air conditioner. Are you familiar with the 460 air conditioner? Let me go to one of my friends here. Let's see. I think I'll start back to Stuart again. Stuart, are you familiar with the 460 air conditioner?
No.
What you do, Stuart, is you roll all four windows down and you drive 60 miles an hour. That's called a 460 air conditioner. Stuart, you're supposed to laugh at my jokes.
I did.
Well, good for you. Well, anyway, that's what I did all summer, and I was miserable. But there's no moving parts or anything. It's just a kind of like a tube with a constriction. But I tell you what they use these for is you'll have liquids coming in, and then you'll have, well, usually saturated mixture coming out. You'll have compressed liquid coming in and saturated mixture coming out. In other words, you're having a change of state. You have a change of state. So that's what throttles do. See, how does it go? Turbines provide power, nozzles speed up, and throttles provide a change of state. So I've told you about throttles, and we're going to work one. Now the one I want to work is, this is 424. We're going to do problem 424 now. And it's a throttle. And there's my device sketch. And when you go to the parts store, they call them expansion valves. And you have one in your refrigerator. Okay, let me find this problem and we'll label our device sketch. 424. Okay. Right. I found it. Methane. Now you got methane, that's CH4. You got methane coming in and going out. It's coming in at 1 megapascal. 1 megapascal, 250 K. K stands for Kelvin, of course. It is throttled to a valve to 100 kilopascal. So no change in kinetic energy. What is the exit temperature? Okay, we're going to find the exit temperature. So there's my device sketch. Now let's draw the PV diagram. Now, what are the rules again about PV diagrams? If there's a vapor dome, I think there is, because see, methane can liquefy. And how do I know whether it's an ideal gas or not? Well, see, if it's got a methane saturated table back here, then it can liquefy. Now, let me see if I can find a methane table. Methane. There's ammonia. Ammonia, carbon dioxide. R410A. R134A. I don't know if I'm going to have any like nitrogen. Maybe they don't have a methane. Let me keep looking. Aha, saturated methane. They have a methane table in the back. The rule is if they have a saturated methane table, that must mean that it can liquefy. That's what they have back here. So that's another way to know. So let me draw the PV diagram. Now it helps me to know where the top of this vapor dome is. I'm on table B.7, and this pressure at the very top is 4599. It's 4599.2 kilopascals. That's where the top of it is. What about the temperature there? Well, the temperature is 190.6. Well, let me write that down. I'm going to save my place here so I can find this again. Yeah. Good going. Yeah, there we go. We'll find it again. Okay, now I need a bookmark here on this table. Yeah, that helps. And now the temperature is 190.6. Okay. So this right here, they got a name for this. It's called the critical isotherm. It's 190.6 degrees Celsius. I found that on table B.7.1. B.7.1. See if you can find that. But now see what we have is 1 megapascals. Well, that's 1,000 kilopascals. That's lower. That's like this maybe. Here's 1,000. 1,000 kilopascals. Maybe I should draw it a little higher. We know we're on the 1,000 kilopascal, but our temperature is 250. Well, this was the critical isotherm. 250 is hotter than that, you know what? 250 is hotter than 190. So here, I'm going to draw the 250 isotherm. Here we go. This is the 250 degrees Celsius isotherm. Am I doing this right? Methane. I'm getting state 1 out here in superheated vapor. 1,000 kilopascals. And
the temperature is 250 Kelvin, not Celsius. So it would be like
oh,
negative 20 Celsius.
I owe a honking thank you point. Now who is that just spoke up? Who is?
Spencer.
Spencer. Spencer. Honking thank you point for Spencer for helping the class. Okay, now Spencer. They said 150. I'm reading the wrong one here. I got lost again. They said 100 kilopascals. Right? 100 kilopascals.
1,000 kilopascals. 250 Kelvin.
Throttle to, yeah. It's throttled to 100 kilopascals.
Yeah.
Well, where did I get this 1,000 kilopascals? What am I doing here? This is not right.
Initially, it's 1 megapascal.
Oh, yeah. It's 1, yeah. No, that was correct. So that part was correct. State 1 is right there. It's state 2 is where I have my problem. It's going to 100 kilopascals. See, this is 1,000. This is 1,000, and 100's down here someplace, right? 100 kilopascals. Now, 100 kilopascals, well, methane, 100 kilopascals. I'm just having senior moments all over the place here. They're in Kelvin, aren't they, Spencer? They're in Kelvin. Okay, so 100 kilopascals. They don't have a 100 kilopascals. They have 101, but it's 111.7 Kelvin, isn't it? Okay. 111.7 Kelvin. Holy cow, that's really cold, isn't it? See, this is 250 K. What's 250 K? Don't you have to subtract 273 roughly? Let me do that.
Yeah. It's like negative 23.15 or 85 or something. Like
yeah,
that.
it's equal to negative 23 degrees Celsius. So this is a screw up. This is negative 23 degrees Celsius. And we're going to somewhere around 111 K. So what would that be? 111, 273. That'd be in, gee, was negative 161.5 Celsius. What do you think? It's down here someplace. That looks like state 2, but the temperature is, it's really cold. It's negative 161.5 degrees. So really cold. But I think you're still in the superheated vapor, maybe. I'm not sure, though. I am not sure. Maybe you're in here. Let me think about it just a minute. We're talking about methane. And we're talking about a pressure of 100. Pressure of 100. Kilopascals. But we don't know what the temperature is, do we? Is that what they want us to find, the temperature?
Yes, they want us to find exit temperature.
Yeah. All we know is the pressure. Okay. Well, to be honest with you, I'm not really sure about my process yet, but when I'm not through, I'm not ready to give up. We've drawn our device sketch. We made an attempt at drawing our process on a PV diagram. Now let's do the first law. Now, when you do the first law, this is going to be 0. This is 0. There's no heat transfer. There's no power. The m dots are the same. We're going to throw out all the terms except the enthalpies. And here's what you're left with. HI equals HE. The throttle is the simplest of all the devices. This is the first law for the throttle. Now we can get the HI because we know the pressure. It's 1 megapascal. We'll look that up here. And the temperature is 250. And it says the H there is 50601. This is 506. I think it's 50601. Yeah. Kilojoules per kilogram. And that's going to equal the exiting specific enthalpy, because we don't worry about any of these other terms. The m dots are the same, and these are 0. And this is our first law. Can you find that 50601? It's on table B.7.2. B.7.2. See if you can find it. I'm getting the specific enthalpy at 1,000 kilopascals. That's 1 megapascal. And 250 K. Yeah. 50601. I think I did that right. So now we know what the exiting specific enthalpy is. All right, here, let me write that down. The exiting specific enthalpy is the same as the incoming specific enthalpy. It's 50601 kilojoules per kilogram. Okay. Now we need to find where that is at the 100 kilopascal table. Do they have a 50601 in there? By Jove, they do. 50601. And you can get the temperature. Now, here's the numbers on the chart there. At 225 K, they have 464.99. And at 250 K, they have 518.27. See, what we want is 50601. We're going to have to interpolate and get our answer, but it's out here. I think we did this correctly. It's out here. It's in the superheated vapor. So that's good. And now we're going to get the temperature. So here goes. We're going to interpolate this now. We need practice interpolating. I want everybody to interpolate this. Isn't 506 in between 464 and 518? So the answer here is going to be in between those. All right, interpolate. Let's see what we get. See if you can get this right. Well, I did that. I wonder if I did that right. I'm getting 244.2. So we think that this temperature here, yeah, but that we need, that's in K. Let me see what 244.2 K is. Let me see what that is. That's minus 28.9 degrees Celsius. We think that this temperature here is minus 28.9 degrees Celsius. So it cools off. That's what the throttles do. They definitely cool off there. I wonder if that's the answer in the book. Let me see if I got that answer right. How about you guys? Are you getting this 244.2 when you interpolate? Now we did 424 is what we tried to do here. And they said the answer is 244. Yeah, we did it right. That is correct. We have drawn the device sketch. We have drawn the PV diagram with the process. We have found the exit temperature. But when you do your homework, by the way, there's homework. Now the due dates are given. So I'm not going to tell you what they are, but they're right there on Blackboard. You can read them. There's There's due dates there. Turn that stuff in on Blackboard and I'll give you some grades for the homework. So we got that one right. And we're gonna do another one. Now let's see what's next here. Let's see. Now that one was SI. We're gonna do a throttle in English now. But before we do, did you have any questions on that? No, nobody said anything, so I guess you're okay. Okay, well, we're going to do another throttle in English this time. So I'm going to erase all this if you're happy. Here's your last chance to ask me anything. All right, well, let's say goodbye to all that. I probably should leave this first law up here. We're going to need it. Yeah, you got some homework, I'm sure. Okay, now the next thing we're going to do is 421. And it's also a throttle. It's R410A. That's what I have in my house. Now, whenever you're given a throttle problem, and I'll tell you what, thermodynamics instructors at OSU or TU, they love to give problems on exams dealing with throttles. The reason is the first law for the throttle is the simplest, easiest first law of all of them. It's just HI equals HE. That's it. You can't get much easier than that. See, here's the first law in general for anything. But when you get through crossing out stuff you don't want, you're left with this. That's all you have left. And the instructors that write these exams figure, look, if a student can't work a throttle, well, then what's the use in asking them something hard? They can't do a throttle, they probably can't do anything. So here we go. We're going to do 421. Let me find it here. Let me shop around and find it. Oh, here it is. Saturated liquid R410A. Now, you know what I start with when I do problems? I start with the PV diagram. And what we're going to do is we're going to find out where saturated liquid is. Well, where is saturated liquid? See, there's compressed liquid, there's saturated liquid, there's saturated mixture, there's saturated vapor, and there's superheated vapor. Do you know where all those are? Oh, yeah, of course we do, Mr. Griffin. Yeah, you know where they are. You know where this saturated liquid is. It's on this line right here. This is called the saturated liquid line on your vapor dome. Okay, well, let me go find R410A. Let me shop around here. Let's see if I can find it. R410A. There it is. And what we want is, wait a minute, I didn't do my device sketch, did I? Well, here, let me do my device sketch. There's my device sketch. And we have M dot coming in. We don't really need the little I and the little E. They're the same. They got to be the same. You can't have more coming in than going out. The thing would explode. For those of you that just tuned in, we are doing a throttle. Problem 421. This is the first law. It's a controlled volume because you have mass going in and mass coming out. And what did they say? They said 25 Celsius. So let me write that down. 25 degrees Celsius coming in and 400 kilopascals coming out. Okay. What's the exit temperature? Find the percent increase in the volume flow rate. Well, we'll get to that. All right. Yeah, but where are we on here? Well, let's find the R410A. I think I just lost it. I had it. There it is. We want 25 Celsius. Well, 25 Celsius is about in here someplace. Let me find my red. Oh, gee, I think I dropped my, here it is. "25 Celsius is in here someplace. There's your 25 degree Celsius isotherm. And here is our, call it state 1, or the incoming state. There's your incoming, there's your exiting. And we're right there on the saturated liquid line. And I can tell you what HI is. Just look on your table. Let's see what it says. It says for 25 Celsius, it is 25 Celsius, 9759. 9759 kilojoules per kilogram. Now I need one of my students to say that they can find that. Can you find it? Find it. I need somebody to back me up here, because I think twice today I've goofed up and written the wrong number down. Do I have the right number for the incoming specific enthalpy? Do I? I need an
That's what I'm seeing.
Yeah. Now is that my friend Stuart?
Yes.
Well, that's what I got, Stuart. Now here's the dirty little secret. That's equal to the exiting. The exiting specific enthalpy is equal to that. See, look at here. The incoming specific enthalpy is equal to the exiting specific enthalpy. So if you know the incoming, well, then you know the exiting. Isn't that simple? Isn't that nice? Now, we also know that this is at 400 kilopascals. Well, I'm curious, what is this pressure here at state 1? Let me find that. That pressure is 1653.6. 1653.6 kilopascal is state one, but we're going to go to 400 kilopascals. Well, 400 is down here someplace. I don't know. Somewhere down here. 400 kilopascals. We know that we are on the 400 someplace. Let's look up and see what these are. Now this one here, at 400 kilopascals. Gosh, they have a 399.6. That's close enough to me. I'm happy with it. That value right there is 2824. 2824. We're talking about HF. And this value right here is at 400 kilo. It's 271.89. 271.89 kilojoules per kilogram. Kilojoules per kilogram. Now, what we've got is 97.59. Well, you know what? 97 is in between 28 and 271. We're in here someplace. Here's state 2, and here's our process. Now later, we'll start talking about irreversible processes, and you'll discover that you're supposed to use a dashed line for that one. But don't worry about that now. We'll get to that later. But there's your process. There's state 1. There's state 2. There's your process. It's really kind of a curve. It's not exactly a straight line. And you have an arrowhead right there. So what? Well, I can get the temperature. I can get the temperature just reading it off the chart. They've got 399.6. You know what? That's minus 20. According to the table. I tell you what table I'm at. I'm on table B.4.1. I'm on table B.4.1, and I believe what I just said was this is minus 20. This isotherm going through here is minus 20 degrees. Would it be Kelvin or Celsius? I don't know. Let me look it up here. I think it's Celsius, yeah. It's minus 20. Yep. Well, let's see if I got that right. I got an answer book here. And we'll see if we got that one right. What was that problem? That was, guys, we just did 421. 421. You guys need to get you one of these answer books. That way you wouldn't have to think. You could just copy it down. That'd be good. Except, then you really wouldn't learn anything. That's the down part. Now, the answer they have in the answer book is minus 19. This is what they have in the answer book. I can't. Minus 19.98 degrees Celsius. And I just put minus 20 on there because, see, I didn't interpolate. To be honest with you, the book has, I think, 399 kilopascals back there. And what we got to have is 400. So I was too lazy to interpolate. But minus 20 is good enough for me on that. So you went from saturated liquid to saturated mixture. You changed your state. You got more vapor that way. Do you understand? Got more vapor. Now they wanted us to do something else, so let's do that too. I'll put this down. We can check our answer on that in a minute. Where are we going to do it? Well, there's lots of room up here. Now, to do this other part on this problem, I'm going to need the quality. So here, let me make a little room here. You guys know that the quality at state 2 is equal to HF plus the quality at state 2 times HFG. Now we know the quality at state 2. It's the same as the quality, I don't mean that. We know the specific enthalpy at state 2. It's the same as in specific enthalpy at state 1. Look at here. And we know what that is. It's 97.59. 97.59. Now we're going to look these up. And remember, we're at 400 kilopascals. Well, they don't have a 400 kilopascals, but they have a 399.6. That's pretty dang close. And we're just going to go with it. That's close enough for me. 399 points. That's 2824 plus the quality at 2 times minus. I just had a senior moment. What are we doing? We're finding, 399.6. That's close to 400 kilopascals. This is 243.65. Can you find these numbers here on table B.4.1? I need somebody out there to double check and make sure I got those numbers right. Now, when you're doing your homework or an exam, whether you're here with me or with OSU or some other place, write down the table number where you got the answer. Sometimes that'll help. The instructor can look at that and say, oh, they used the wrong table. They were using English. They looked up stuff in the English table. This student really knows what they're doing. It's just that this is not English. This is the metric stuff here on this problem. But write down the table number. That might help your grade. It'll help you when you go back over it to try to see where did I get that number? Where did I get those? Okay, now let's find what the quality is at 2. Here goes. The quality at 2 is I'm going to find the quality at 2. Did you get a 0.2846 quality at state 2? Anybody? Anybody get that?
I got that.
Yay, I bet it's right. Now, what we're going to do now is we're going to get the specific volume. Just need a little room here to get that. And then we'll finish our problem. The specific volume at state 2. Well, you know how to do it. It's the little VF plus the quality at 2 times VFG. Okay. Well, what's the little VF? Okay, well, you look in the table. And they wanted 400 kilopascals, but we're using 399.6. That's dang close. So what you got here is 0.000803. 0.00803 plus the quality of state 2, which we know, 0.2846 times VFG. VFG is 0.06400. 0.06400. Okay. Hopefully I got those numbers right. But I hope you guys, somebody out there is checking me. Okay, I'm going to find the specific volume at state 2. Here goes. I'm doing it now. 0.00803 plus 0.2846 times 0.06400. Did you get 0.0190 blah, blah, blah? So now we have the specific volume, and we're going to finish our problem. I just need some room to finish it here. How about right here? Now, what did they ask for? Let's read and see what they wanted us to find. We're doing problem 421. It's a throttle, and it's using refrigerant. Is it using a refrigerant? Yes, it is. It's using refrigerant R410A. They want the percentage increase in the volume flow rate. Here's what they want. They want us to take the final volume flow rate and subtract the initial volume flow rate and divide by the initial volume flow rate. And then to find percentage, don't you always multiply by 100? Isn't that what they want for their answer? If you want to find the increase, percentage increase in something, that's how you do it. You take the final minus the initial, and you divide by the initial, multiply by 100, and you got the percent increase. That's what we want. Well, how in the heck are we going to get that V dot thing? Well, there's a formula for it. It goes like this. I think, let's see, big V is equal to M times little v, right? Right, Mr. Griffin. See, big V is equal to M times little v. Now watch this. If you put a dot over that, big V dot is equal to M dot times little v. Yeah, that almost makes sense. Okay. So here's the plan. This is going to be equal to M dot times little v 2 minus M dot times little v 1 divided by M dot times little v1. Did that make sense? Oh, don't forget times 100 to get the percentage. Hey, you know what? The M dots are all the same. The M dot they don't have an M dot I and an M dot E on this because they're the same. You got to have the same mass flow rate going in and the same mass flow rate going out. Else, if they had more coming in than out, it'd blow up. Don't want that to happen. Hey, look at here. We can do a little algebra trick here. All we got to do is subtract these. I think we know what they are. I know what little v2 is. It's sitting right here. There it is. I forgot the units, but they're cubic meters per kilogram. What about V1? I think V1, I think that number there is V1. You know what? That's, yeah. I think that number right there is V1. So let's put those numbers in there and we'll get it. Here goes. Just need some room here to write this down. V2 is 0.01902. V1 is, we think, 0.000803. I think so. And then you divide by 0.000803 and you multiply by 100. And you should get your percent increase in your volume flow rate. Well, let's see what that is. Here goes. 0.01902 minus 0.00803 divided by 0.00803 times 100. Holy cow. This is the kind of interest rate I wish I had at my bank. Is 269%. 2,269% increase. Now let's see if that's the right answer. I got an answer book here. What problem was this? 421. That's not the answer they got. So something bad happened. Let's see. Let's see if I can figure out what they did. They got this 0.019. They agreed with us on that. Yeah, they agreed with us on that. But they said the incoming at 25 Celsius. Oh, I did the wrong thing, guys. What I need is the specific volume here at state 1. I screwed up. The specific, I don't want the specific volume here. That's not state 1. State 1's up here. So this number is not right. Let me get the right number. So I goofed up there. That's not the right answer. What we need is the specific volume at state 1. Now, did we have it already? I forget. Was that it? 28, 24? I don't know. Let me go to my table and we'll look and see. What we want is at 25 Celsius. And what we want is 25 Celsius. And at state 1, it's 0.000944. 0.00 25 Celsius. 944.0000944. There we go. See, it's state 1, the specific volume at 25 degrees, according to the table, for saturated liquid on table B.4.1. I'm getting this number on table B.4.1. And now I'm going to plug that in. We'll get the right answer. Here goes. See, what I did was I plugged in the specific volume here, but that's not state one. State one's here. Okay, here goes. 0.01902 minus 0.000944 divided by 0.000944. Okay, times 100. I'm getting roughly, rounding it off, 15% increase. That's a 1,000. It's almost 2,000% increase, which means that it got bigger by about a factor of 200. And that is the correct answer. Now wait a minute. For some reason, the book got 1913% increase, and I got 1915. Let's don't fight over it, okay? Maybe I rounded off or they rounded off, but I think, yeah, somebody rounded something off someplace. But that's pretty dang close. Okay. In other words, your volume is increasing like crazy. You know why? Because this is all liquid and this is, well, it's 28% vapor. It's still got a lot of liquid. Well, what is 28 from 100? 72? Here at state 2, we're still 72% liquid, but we're 28% vapor. Did you know when you evaporate or boil from a liquid to a vapor, the volume increases by a factor of around the ballpark about 1,000? So if you have if you have 1 cubic meter of water and you boil it, you will have 1,000 cubic meters of steam. It's incredible. So we're increasing our volume by 1,915%. So we did good on that. Now here's how you do these problems. I wanted to show you this. Let me show you this. In this book someplace, they have a step-by-step problem solving. See if I can find it. The way to solve thermal problems. They tell you in here, it's step by step. It's a foolproof plan. Let's see if I can find it. Oh, gee. Can somebody help me find that? I'm having trouble. Yeah, here it is. It's on page 80. Before we do that, I've still got 15 minutes with you guys. I think what I want to do now is worth doing. Did you have any comments or questions on problem 421, the throttling problem? Anyone? Well, nobody has any questions, so I'm going to erase all this if I can. Say goodbye to all this unless you have a question. All right. Yeah, now in your book on page 80, is a step-by-step step-by-step method to solve thermal problems. Now, I've been doing this every time I do a problem. I've been doing this, but it's worth going through. Step number 1, make a sketch of the physical systems, illustrate all mass flows, heat flows, work rates, blah, blah, blah. You know what I call that? I call that the device sketch. Haven't I drawn device sketches for you guys? And haven't I labeled them, put the pressure or the temperature or whatever? Label them. Label them with temperature, pressure, M dots or whatever. Whatever is given, label them. Heat transfers. Power, if they give it to you, label them. Okay, number 2. You got to decide whether it's a control mass or control volume. You must decide whether it's a control mass or a control volume. Like that problem we just did was the throttle, that was a control volume. But in chapter 2, well, wasn't chapter 2 all control masses? I think so. Yeah. Well, no, chapter 3's got control masses. It's chapter 4. It's chapter 4 that has the control volumes. But you got to decide which it is, because see, the first law is different. You have to decide that. Number 3. Write the general laws. Here's where I differ from them. See, they want you to go to writing down this first law of thermodynamics, but I would write the PV diagram. I would try to write the PV diagram, and I would try to put the process on my diagram. And I would try to label it too, label it with the temperatures and pressures and whatever we got. And then they said the equations. Okay, well, that's fine. You can do the first law. That's fine. Now, somewhere in here, you got to decide, is this going to be an SI or an English problem? That one that we just did, I forget the number on it, but I believe it was SI, because we had kilopascals and cubic meters and so forth. Okay. Now somewhere in here, you got to decide, well, actually, you need to decide right here. You need to decide, is this an ideal gas or a real gas? If you were tuned in earlier, one of my excellent students asked me a question about that, and I told them that you got to decide, is it an ideal gas? So then you draw a, what do they call those, hyperbolic isotherms. If it's a real gas, then you draw the vapor dome. Okay, and then let's see. So here, see, if it's ideal gas, you'll do the ideal gas law, for instance. But if it's not an ideal gas, well, then you don't use the ideal gas law, okay? You have to, we had to decide that up here someplace. And then what? Wait, the rest of the structure. Well, sometimes there's other equations. I'll try to show you problems that deal with other equations sometimes. And then what? Do the math. Okay. Running out of room here, but you're going to do the math. We've been doing math. I've been pushing my calculator a whole bunch here this morning, and I'm hoping that you guys are pushing your buttons right along with me. Do the math. Step 8, you check your work. Now, there's several approaches to checking your work. If you're working with a friend, the two of you together can see if you got the same answer. If you're lucky enough to have an answer book, like I do, then you can check it that way. But there's also just checking your work with common sense. Like we were doing a problem, and one of my excellent students helped me out and said, Mr. Griffin, I think you're doing it in Kelvin or in Celsius, and it's supposed to be in Kelvin, for instance. See, don't get those mixed up. In fact, I think I've told classes before, the difference between an A and B students in this class is the difference between Kelvin and Celsius. Because if you get those mixed up, you get the wrong answer. And like if you're doing something and you're finding the pressure, well, keep in mind what atmospheric pressure is around 100 kilopascals, or what, about 14.7 psi. You should know that. So if you're solving a problem, kind of relate your pressure to those values. And if you get you're doing the pressure in a room here with students, and you come up with a pressure of several thousand kilopascals, well, we'd all be dead. So use a little tiny bit of common sense and look at your answers. That's another way of checking your work. So there you have it. Also, when you check your work, I want you to check your units. Put that in step 8 also. Remember, today I've given you these problems where, I forget what we had to multiply by, 32.174 and 778.17. Remember that problem? You had to do that to get the units the same. You got to be careful about your units. Okay, we've had a wonderful time. And what I want you to do is to do your homework. And I want you to read chapter 5, because we're going to be in chapter 5 on Wednesday. So read chapter 5. for Wednesday. Do your homework. Our time, it's sad, but our time is running out here. Do you have any last comments or questions for me before we say goodbye?
Yeah, I was curious if you got my email,
Now, who am I talking to?
Parker.
Parker. Let
Hmm.
me make a note here, Parker. I can't remember if I did or not. What was it about?
It was about the homeworks.
Okay. What did you want to know about the homework?
Well, so we only get like one submission attempt for the homeworks, right?
Oh, that's a good question.
And I accidentally I submitted the assignment and then I realized I did it wrong.
Well,
And
do it again and submit it to me on my email, on the email, Parker. Okay.
okay.
But yeah, the answer is on Blackboard. You just get one chance. You're right.
Mhm.
Now on my homework, I'm pretty generous. I don't give you a 0 on the homework. I'll give you like 2 out of 4 if you mess up, but don't mess up. Anybody else before we say goodbye? Anybody else? Read chapter 5 for Wednesday. Do your homework. Anybody else? Last call. I'm going to sign off. 5, 4, 3, 2, 1, 0. Bye-bye, students. See you on Wednesday.